Todavía confío.
Alrighty, hi everyone. I hope we're doing okay today on this Sunday. We'll get started right away at 6, or like 6:01, so we'll get started. I know we only have an hour here, so as the screen says, if you have a question, please just throw it in the chat. Some people were here a little bit earlier and I already have some in there. So it's looking like we need number 12 on mock exam 3B. And then I think that's mostly like the percent of carbon, oxygen, and nitrogen that we're looking at. So if we could, well, I'll start there. So I think we see most of that. And then I think some redox and oxidation stuff that we're looking for is going to be the important stuff. Okay, I'm sorry about that. Hold on. Get down.
Yeah, let's see if that kitten climbed up the stairs.
Alrighty, so we'll start with the mock exam question 13. Mock exam B question 13. So that one is going to be, let me pull it up on my computer. We're looking at it. It is
Taryn was kissing you yesterday.
It's not a kid, that was a cat.
we are looking at the combustion of a carbon, oxygen, and nitrogen sample.
It's like a teenager.
Yeah, I mean, it's shown up yesterday. We don't know where it came from. Stop it.
Okay, so Okay, so this question starts off like this. You can hear. Hold on, give me 1 second. Is this better? No, I can still hear myself in 2 seconds. Okay, give me 1 moment. I'm so sorry. Okay, I think that should be better. Okay, so this question is question 13 from Exam B. And so this is the combustion of a carbon hydrogen and oxygen compound. So what's important here is that when we look at the combustion of a carbon, hydrogen, or oxygen compound, we know that we're going to have some form of equation where it is C in a number, H in a number, and then oxygen in a number. And with combustion analysis, we always know that oxygen is being used to produce carbon dioxide and water. So when we look at this, we have to recognize that the carbon from your compound only goes to the carbon in your CO2, and the hydrogen from your compound only goes to the water in your H2O. So anything that is in the carbon portion of your CO2 is going to be from this carbon portion here, and anything from your hydrogen portion in your water is going to be from your hydrogen here. So can anyone tell me the first thing that they had to do for this question? Does anyone know where we would start if you're looking at question 13, mock exam B?
You take your grams of CO2 and then you convert it to moles. And then you use a mole ratio to convert the moles of CO2 to carbon. And then you do the same thing for H2O.
Perfect, right? So we have to take our grams of carbon that we have from our CO2 and convert that to moles, and then the grams of our hydrogen and convert that to moles for hydrogen as well. Right, again, we like to work in moles, so that's going to be our first thing. So we're given that we had 2.80 grams.
Why is that taking so long?
Sorry, 2.805 grams of CO2. We're going to use the molar mass to get to moles. So we have 1 mole of CO2 is equal to 44.01 grams of CO2.
Why is it cold?
And then how many moles of CO2 are in 1 mole of, or I guess how many moles of carbon are in 1 mole of CO2? What is that ratio?
1.
Yep, it's going to be 1 to 1. So we have 1 carbon for every whole 1 molecule of carbon dioxide. So we'll have 1 mole of carbon is equal to 1 mole of CO2. Even though this is 1 to 1, you still want to show that on your exam because we want to make sure that you know that there is only 1 carbon per 1 CO2. Right, and if we stop there, that's usually where I stop for a moment to grab the moles of CO2, or to grab the moles of carbon, excuse me. So I got 0.06374 moles of carbon And then do we need to get to grams of carbon in order to solve this entire question? Good. Yep. So we do need to get 2 grams, and we're going to use the molar mass of carbon to get 2 grams. So then we'll do 12.01 grams of carbon is equal to 1 mole of carbon. And so we end up with 0.766 moles of carbon. Okay, and we're going to do the same thing for hydrogen. So in order to set that one up, we have 0.6936 grams of H2O. 1 mole of H2O is equal to 18.02 grams. What's our mole ratio here for hydrogen to water? Good, right? We have two waters or 2 hydrogens for every 1 water. Oh, yes, sorry. This is grams. Okay, so we have 2 moles of hydrogen for every 1 mole of H2O. Again, we're going to get the moles of that. So we have 0.0770 moles of hydrogen. And then again, using the molar mass, we'll have 1.01 grams of hydrogen is 1 mole. And so we end up with 0.0778 grams of hydrogen. Okay, questions how we got to grams of carbon and grams of hydrogen then so far. That makes sense how we got there? Okay, so now once we get here, we have to know what this tells us. And so like we said, all of the carbon that we had over here, all of these grams of carbons has to go to our grams of carbon in our original compound that we are combusting. And then all of our grams of hydrogen have to go to the grams in our hydrogen compound that we are in our compound that we are combusting. So what does that mean for how we can solve for the oxygen grams? What do we know about that? Or how are we able to get to the oxygen grams?
We have to do like the empirical things, like is that the mass to mole divided by small, that kind of thing?
We will eventually have to get there, but we need to know how many grams we have first. So
Okay.
that's going to be our step right after we get to, right after we're going to subtract from the total. So we know from our question that we're given a 1.047 gram sample. So we're going to subtract the carbon and the hydrogen that we just found because we know that has to be in our sample. So we're going to subtract the sum of that. So we'll have 0.766 grams and 0.0778 grams. And so that means we're going to end up with 0.2037 grams of oxygen.
Everybody gets
Okay, does anyone have any questions on how we got to the grams of oxygen?
yeah, where did you get the 1.047 grams from?
That came from the question. So on your actual exam, in the question, it says that you are combusting a 1.047 gram sample of compound.
No, it's mute.
So on mine it says 0.1804.
Are you looking at mock exam A or mock exam B?
It says A, but when I was looking at B, it didn't have it on question number 13.
Oh, I'm sorry. This is question 12 from question B. Oh, I'm so sorry.
Oh, okay.
That's my fault. Question 12. Okay, so do you see where you found that start then? Okay, so now we have our grams of oxygen. So now we're going to do where we have to divide by the smallest number of moles. So we have the moles of carbon here, and we have the moles of carbon here, or moles of hydrogen here. Now we need to use the grams of oxygen we just found to get to the moles of oxygen. So same thing, this time we're going to use the molar mass by dividing because we need to get to moles. So say 1 mole of oxygen is going to be 16.00 grams of oxygen. And so we end up with 0.0127 moles of oxygen. Okay, so what has the smallest moles of oxygen, or what has the smallest moles between carbon, hydrogen, and oxygen? Good, oxygen has the smallest number of moles. So we're going to divide all of our moles by the smallest number of moles. So I'm going to do that in this top corner over here. So we'll take 0.06374 moles and divide this by 0.0127, 0.0770 divided by 0.0127, and 0.0127 divided by 0.0127. Okay, so we're taking each of our moles that we found previously in the question and now dividing it by our smallest number of moles. Now this is going to tell us the ratio of our smallest to our other compounds, right? So we end up with about 5 here for carbon, about 6 here for hydrogen, and 1 here for oxygen. Okay, so do we need to multiply by anything to get to our formula, or is this okay to use? Yeah, good. It's good to use, right? So now we have C5H6 oxygen. Okay, so this will be our final answer for that mock exam B question 12. Okay, so if we were to just recap what we did here. Okay, good question. So we don't need to multiply by anything because our decimals here, the 0.00 after the 5, the 0.04, and then the 0.0, that means that you don't need to like round or anything. If we had something where it was like 0.25, we want a whole number, and that is too big, or that's too far away from 0 in order to round like down or anything. I would say you could probably have somewhere between like 5.0 and 5.1 that will allow you to round down to a whole number. But if you have anything greater like 0.25, 0.33, or 0.5, then that means you have to multiply by something in order to get that whole number. Does that make sense? And yes, this would be the empirical formula. Any questions why we're rounding or when it wouldn't be okay to round? I can show you in another example. So if we had something where if you had 5.0 and you were dividing by 2, right? You end up with 2.5. This here, this 2.5, we cannot round up to 3 and we can't round down to 2. So we have to multiply by 2 in order to get it to 5. So if this was our hydrogens, right? If this was our hydrogen moles, we can't say that we have 2.5 hydrogens. We have to get to a whole number. So we're going to multiply that whole thing by 2. So we end up with 5 hydrogens. But because all of our numbers were nice and had good decimal points, we are able to just use those numbers directly. Does that help on those last questions that were coming in towards the end? Okay, and then good question, Anna. So this was the empirical formula. Okay, if we wanted the molecular formula, they would give you the molar mass of your overall compound. So to find the molar mass of this specific compound, we would take 6 times 12. I'm sorry, not 6, 5. 5 times 12. 6 times 1.01, and then 16, and find this molar mass. I don't know what this is. This is 60. This is 16. Maybe 2, I think. About. Okay. So if they told you that your molar mass of the compound combusted was 164 grams per mole, you would take your molar mass that you have given for your molecular formula and divide that by your empirical formula, and you would get 2, which means you need twice as many things in your compound in order to get to that molar mass. So you would take your C5H6O, multiply everything by 2, and we get C10H12O2. Does that help with those questions? I think exam A, like your mock exam A, question 13 is also one of these questions. So now that you know how to solve one, maybe go through and do that one on your own again if you were having some trouble with that. Use these notes and go back and see if you can get it now. Okay. Any other questions on combustion analysis? Okay, cool. Let's see. I think there was, I'm looking at the chat again. Okay, so let's stick with mock exam B and we'll go to 14 now. So let me see if I can pull this up, if I can share my screen a little differently. Okay, so here is this question. That's question 14. Okay. This has to do with titrations. we are looking at our different acids and our different bases. So can anyone tell me your 6 strong acids that you need to know before we get started with this question? I gave you one of them. Mhm. Okay, good. So those are going to be your 6 strong acids that we have. They're in the chat. If my handwriting is horrible as well. But we have H2SO4, HI, HBr, HCl, HClO4, and HNO3. We have to remember that HCl, HBr, and HI are all in that group 17 row, except for hydrogen fluoride. That is not a strong acid. That is a weak acid. So those are the 6 you need to know. And then I did see an OH minus come in for your 6 strong bases. All of them will have 6 strong bases, but does anyone know like one strong base? What the actual formula for it is? Nice. Yep. Okay, so NaOH is a good one. Barium hydroxide is a good one. Potassium hydroxide is a good one. Good. Anything else? Good. Yep. Calcium hydroxide. And there's one more. What's in between? It's not going to be CSOH. So it's going to be strontium hydroxide. And so when you're looking at the periodic table, it goes hydrogen, lithium, sodium, potassium, and then like magnesium, calcium, strontium, and barium. So your 6 strong acids kind of make this little zigzaggy thing over here. So all those will exist. Those 6 are on the periodic table. So lithium, sodium, potassium, and then go over and go 3 down as well. So that's how you remember your 6 strong bases. And then your 6 strong acids, you kind of just have to know a little bit more. Okay, any questions? Those are the ones that you have to know that she might ask you for. So just want to make sure we all are comfortable with this. Your H2SO4 is going to be diprotic, we called it. And so are your calcium, strontium, and barium hydroxide bases are diprotic as well. Okay, so your question here for mock exam B, question 14. We said that we had 0.284 molar barium hydroxide, and we wanted to titrate 25.0 mils of 0.707 molar HCl. So how many milliliters of barium hydroxide are needed? Okay, so can someone tell me if barium hydroxide is a strong acid or a strong base? Yeah, good. So barium hydroxide is going to be our strong base. And what about HCl? Good, that's going to be a strong acid. Okay, so how are we going to set this up so that we can figure out how many milliliters of barium hydroxide we need in order to titrate the hydrochloric acid? What equation are we going to have to use? Yeah, awesome. Good job, Blake. Right, we need M1 V1 is equal to M2 V2. Okay, so when we're looking at our question, I usually like to annotate and say, okay, what do I know already? So we have 0.284 molar barium hydroxide. Is that going to be, is that M1 V1 or M2 or V2? Or is that concentration helpful? Yeah, sure. We can call it M1, right? We can call this M1. What about 25 mils? Is that, what can we denote that as? Good. So if 0.284 molar is M1, good. Then we want it to be V2, right? Because the 25 milliliters is talking about the acid. So we want to make sure that we keep our M1s and V2s either with your acid or with your bases. So even though it's the first volume we see, we're going to use that as volume 2. So this will be V2. And then what about 0.707 molar? What is that one going to be? Good, and that'll be M2 because we know that we have the V2 of the 25 milliliters. So now we can use our equation. So we have M1, we said was 0.284 molar times X, because we don't know what V1 is, that is what we're looking for. We have 0.707 molar times 25.0 milliliters. Okay, is there anything else we need to do to this equation in order to solve it? We actually don't need milliliters to liters here. We are using milliliters in both of our answer choices. So we're given milliliters and we want to know the milliliters so we can keep those together. Those will stay the same. Even though they don't cancel out in like moles to liters, they will cancel out using algebra later on. So we can keep our milliliters as milliliters. What else do we need to look at? Okay, good. So couple good things came in here, right? We said make it balanced because of the diprotic base. And then there's 2 moles of HCl, I think, question mark. And then not sure I went through, but we got 62.2, which is twice the correct answer. Okay, so we do need to use a 2 in there somehow. We need to make it balanced. So if we look at this, we have, if we write out the equation, excuse me, color. So if you write out the equation, we have, BaOH2 plus HCl. What is going to form? What are our products that get formed? Good, so we have BaCl and H2O. So how do we balance this equation? I saw one person come in with it. Good, so we need 2 HCl and what else? I think someone wrote it up from 2 H2O. Yeah, perfect. Okay, so now that we have a balanced equation, we know that for every one thing of, or one compound of barium hydroxide, we need 2 hydrochloric acid. So when we look at this, we're going to take, for every 1 mole here, we need 2 moles here. But it's going to be the reverse when we do the titration. So instead of writing 2 over here, we're actually going to divide by 2. Oh, that's a good question. We might need to do a little bit more balancing. It might be, oh, excuse me. Yes, that's right. This is 2. So we're going to divide by 2 because at the equivalence point is what we're solving for, right? When we balance out the base to the acid, your moles are equal. So in order to, when we're dividing by 2, we're making it equal so that we're saying, okay, we usually have 1 mole to 2 moles. So now we're going to go 1 mole to 1 mole. We could multiply the barium by 2 and we would still get the right answer. But we're going to go 1 mole to 1 mole. So you just take the coefficient in front of your higher thing in your acid base and do the reciprocal of it. So that's where we're dividing by 2. Does that help make that sense a little bit, right? If we took the reciprocal of the 1 that's in front of the barium hydroxide, we're also dividing by 1 here. Here we're dividing by 2. Does that make sense, or do you want a different explanation for it? Barium is going to have a +2 charge and chlorine will have a -1 charge. So that just balances it out in terms of the subscript for 2. When you're doing this, as long as you have a balanced chemical equation and you use the reciprocal of your coefficient, that will get you to the correct answer every time. So if you have to do that with like 2 to 3 or 1 to 4, that will, as long as you use the reciprocal, your moles will balance out. Okay, so if you do it this way, then you do end up getting 31.1, I believe, if I remember correctly. We're dividing by 2 because of the HCl. So we're just looking at that left-hand side of the reaction. We don't really care about the products here. I will always say to make sure your equation is balanced before you do the work. Whether that be for your combustion analysis or percent yield, limiting reagents or anything, always make sure your chemical equation is balanced first. So she might have you like predict the products here and then expect you to balance it, or she just will give you a balanced equation. I believe there is a way to solve this for using dimensional analysis, but that gets very complicated because you need to solve for the number of moles that you have. So it is possible, it's just a little bit more steps, and it's a little bit less straightforward than using the M1V1 is equal to M2V2. But it is possible to use dimensional analysis. You have to use like moles. You have to use your concentration and volume to get to moles, and then compare the moles, and then use the concentration to get back to what you need. Which is essentially what M1V1 is equal to M2V2 is doing, just in one equation rather than multiple steps. Yes, Blake. So if this barium hydroxide had a 2 instead, oops, then that would also be divided by 2, right? So if we had something where it was H2SO4 plus NaOH, what would be divided by 2, or what would be divided by in this case? So if we predicted the products, right, what is going to be our products of H2SO4 and NaOH? We know that this is a strong acid. We know that this is a strong base. Good, so we'll have Na2SO4, and what else? Good, and water. So how do we balance this? Good, so we have 2 NaOH, and then I think we also end up with 2 waters on the other side. So if we were to solve this up, is our base or our acid going to be divided by 2 in this case? Good, right? Our base would be divided by 2. So we would take the M of the, the molar of the acid and the volume of the acid is equal to the molarity of the base times the volume of the base. And your base would be divided by 2 here, because we're taking the reciprocal of the coefficient. Okay, what questions do we have for this one? Feel a little bit more comfortable with titrations? Yep, perfect, Blake. So if H2SO4 for whatever reason had a coefficient of 3, then we would divide by 3. Yep, perfect. Rebecca, yes, you absolutely can. The dimensional analysis, you can definitely do that. It's basically what you're doing with M1V1 is equal to M2V2, just in more steps, but you can definitely do it that way as well. Yep, you could divide by both sides in the same problem. And if they both had the same number in front, then you just divide by the same number. But that probably means that you can reduce them later on, or those cancel out anyways, right? So if we had something where we had M1V1 is equal to M2V2, and we both were divided by 2, these do end up canceling later on down the road. So you can just do the math as normal. But yes, whatever the coefficient is in front of, you can divide by. Nope, you will not be. The only case you would be multiplying by 2 is if the coefficient was a 1/2, right? Use the reciprocal, then multiply by 2. But in this case, you'll probably only have a 1 or a 2 that you need to divide by. Yes, Desiree. Yep, perfect. Yep, so if there was a 3 in front of the acid and a 2 in front of the base, you'd be dividing by 3 for the acid and dividing by 2 for the base. Perfect. Yep, that looks good. I think based off of the chat, y'all are feeling a little bit more comfortable with that. Yep, you're trying to get one mole to 1 mole of both of them. We're trying to compare mole to mole. And so we're saying, okay, we have in terms of the barium hydroxide and the, what do we use? Hydrochloric acid, right? We have 1 mole of base to 2 moles of acid. So we're dividing by 2 to get to 1 mole of base to 1 mole of acid.
Miss Allison,
Yes.
would we be able to go into the number 12 on mock exam A?
Yep, absolutely. So I'll do a couple of like just stuff with that as well. So mock exam A is looking at rotations of bonds. So you can either have, I'm just going to do carbon-carbon bonds. So you can do carbon to carbon, carbon to carbon, or carbon to carbon. Okay, so we have a single, a double, or a triple bond. Anytime you have a single bond, it can rotate. Okay, what is another name for a single bond?
Sigma.
Yep, good. So we can have a sigma bond. Are there any pi bonds in a single bond? Good. There are no pi bonds in a sigma bond. So when it's just one singular bond, right? So we can look at carbon to hydrogen, you can look at carbon to fluorine, anything sort of something like that. Anytime you see one single bond, that can rotate freely. Whenever we have a double bond, we can no longer rotate. Okay, and same thing for triple bond. We cannot rotate. You cannot rotate for those. Okay, how many sigma bonds are in a double bond? Good, there is 1 sigma, and how many pi bonds? Good, and then 1 pi bond. What about for a triple bond? How many sigma bonds are in the triple bond? Good, 1 sigma. And how many 2? Good, everyone knows, 2 pi. Perfect. Okay. So that should help with the counting of them. So your first one will always be, right, if you're looking at a big triple bond, this first one will always be a sigma bond. And then these 2 here will be a pi bond. Okay, so if you draw the Lewis structures on mock exam A question 12, you will realize that the C2H4, I think it is. Yes, will look like this. And so since it has a double bond, it cannot rotate. However, these could rotate. Yes, yep. So then going off of that, hold on, look at the 25. So rotate just kind of means like it's spinning on an axis, or on an axis. You can kind of think of it as like a tire on a wheel. It just means that it's free to move around and go in circles. You can't do that with a double or a triple bond due to bonding. And then so why there's so if you're looking at this question over here, this is like the start of number 11 on mock exam A. This oxygen and hydrogen bond actually looks like where that oxygen is bonded to the hydrogen. You need to have some sort of bond between them. So for like the CH2, it actually looks like CH H, and then these other bonds. So that's where you're missing those couple up there. Yep. And then Blake, you're correct with that. If it's just an M1 V1 equals M2 V2 for like a dilution, then you don't need to divide, but it's just for titrations that you need to divide.
Miss Allison?
Yep.
Sorry, on the one that you're on, like the one that still has the rotation. So I get
Yep.
why it can't be rotated, but don't understand why the answer wouldn't be D, because doesn't oxygen and hydrogen have a double bond?
Oxygen and hydrogen.
I'm sorry.
For D,
Wait. Oh, wait, no, it doesn't. So lone pairs don't, it doesn't matter.
nope, lone pairs do not matter.
Okay. Okay, thank you.
Yep, does that help? So then for hybridization, we're going to be looking at the electron domains. So if we have 2 electron domains, that could be something where it's like HC, right? If we're looking at this carbon 1 here, how many electron domains do we have? Good. So you have 2 electron domains for carbon 1 here. This is your first electron domain. This is your second electron domain. So does anyone know what the hybridization is for carbon 1? Good. It's going to be sp. So basically, whatever your electron domain number is how many hybrid orbitals you need. So if you have 3 electron domains, what's going to be your hybridization? Good. This is going to be sp3 or sp2. Good. Yep. And each lone pair is its own domain. So if you had something that was like this, that would be 3 electron domains, or I guess that would be 3 electron domains. Okay. So same thing, if you have 4, then it's sp3, 5 is sp3d, and 6 is sp3d2. So for your acids and bases, I would remember the strong acids and strong bases we went over. Those 12 you should know. 6 strong acids and 6 strong bases. And then for the polyatomic ions, whatever lecture that was, she highlighted a few of them. I think like 10 to 12 on a chart. So then I would remember those 10 to 12. Yes, so this d orbital for the hybridization is just that next highest orbital that we can go into, right? We name everything by S, P, D, and F. So we only have 3 p orbitals that we can fill in. So we have to go next to the d orbital, right? We only have 1 s orbital, so that means that the next hybrid orbital that we can go to is a p. So we fill up the s first, then we fill up the p first, and then we fill up the d orbital. So that's why d comes into play for 5 and 6. Yes, Lena. So if you had something where very similar to the question we had, but instead they gave you like a volume first and asked to find the molarity of barium hydroxide. Right, if you're looking at this one, and instead of giving you 28.4 molar of barium hydroxide, they gave you the volume, you would still need to divide by 2 on the hydrochloric acid in order to get to the correct molarity of your barium hydroxide. Yep, of course. Okay, let's look at 9 and 11 on exam B real quick. Okay, so 9 and 11. Okay, so 11 real quick. So this one is looking at iron chloride, and they give you that you have 2.77 molar. So we know that iron chloride is going to be soluble in solution. So this is going to break down into just the iron ion and the chlorine ion. But is this equation balanced? No. What do we need to do in order to balance this equation? Good, we need 3Cl here. Okay, so for every, what is our mole ratio of iron chloride to chloride ions? Yep, so there's 1 to 3. So we have 1 mole of FeCl3 to 3 moles of chlorine minus. Okay, so we could do this the same way we would do it for a regular dimensional analysis. We could say we have 2.77 molar of iron chloride. We could say we have a 1 iron chloride to 3 Cl minus, which means we have 2.77 molar times 3 chlorine ions. So that gets us to 8.31 molar Cl minus. Okay, does that make sense for question 11? Okay, awesome. And then the last one I probably have time for is question 9, talking about percent yield. So this one here, already gives you your limiting reagent. Sure, we can do. Would you rather? Okay, so would you rather see a bullet point list of certain things you should know, or go through the percent yield question list? Okay, let's do that. So definitely know percent yield. This is your theoretical, I'm sorry, experimental divided by theoretical. Your theoretical yield will come from your limiting reagent. And then your experimental comes from something you did in lab. Okay. So going off of that, you want to know limiting reagent. You'll be able to tell if something's a limiting reagent question if you're given both like grams or moles of products and you have no information about your reactants. That's a very good sign. And right, this is like our sandwich question. It's how much makes the little amount. And there's 2 ways to solve this. You can see what your, limiting reagent is limiting reactant. But there's 2 ways to solve this. You can either see like if you have enough of each of your reactants, or you can solve for how much product can be produced by your reactants. Whatever one is smallest will be your limiting one. You want to know combustion analysis, I guess I'll call it. So this is, and then like determining empirical formula of a CHO compound. Okay. You want to know your sigma and pi bonds and properties. And you want to know hybridization. You want to know your solubility chart or how to use it. You want to be able to predict your products. Let me look at exams. You want to know your net ionic equation. So 8. You want to know like redox number determination. Let's say we need to know titrations. We also want to know dilutions. This one will use M1V1 is equal to M2V2. This one also uses M1V1 is equal to M2V2, but this will be one to remember the coefficient. And then we just want to make sure we can balance our equations. Yep, your solubility chart will be on your exam. And then your redox is redox number determination. So like if you're looking at like Fe solid, you want to know that that has an oxidation state of 0. Like, so your oxidation states, I guess, is a better way to say this. And you don't need a dilution or you don't need a coefficient for your dilutions. And I think that's the big stuff. There are obviously many questions that can be asked from these types of questions or from these big topics, but I think these are the big topics that you will see for your exam tomorrow. With that, it is 7:02. I am recording this, so I will put it on YouTube and send the link to Dr. Altomos as soon as it's ready. I will be up, so if you do have emails or do have questions, just send me an email. I'd be happy to answer them. And then Dr. Altomos has her office hours right before the exam tomorrow from 11:30 to 12:30. Other than that, thanks for coming by. Have a great night. Make sure you sleep. Make sure you eat dinner. And good luck tomorrow. I'll be there. Thank you.